To the next presentation about secure and accurate summation of many floating point numbers, being presented by Marina Blanton. Take it away, Marina.
All right, good afternoon. This work is joint work with Michael Goodrich, who is at UC Irvine, and also
I'm terribly sorry to interrupt you again, but I think the microphone again is off.
Is it better? Like if I talk like this? So maybe we need to raise it. Is this better? Is this better? Yes. So I can turn, right? Yeah, I think so. Like this? All right. So I would like to do this talk, which is joint work with Michael Goodrich, who is at UC Irvine, and Chen Yuan, who was at University of Buffalo. He was my former PhD student, and now he is in Facebook/Meta. So this talk about summing a large number of floating point values, but we would like to do this securely, and I would like to do this accurately. So before I move on, I wanted to sort of give a brief overview of floating point introduction, because this is where our starting point is. So, in general, for a floating point representation, we're going to store basically a triple, and I highlight those values here. This is, as everybody knows, the most common type of computing with real numbers, where we have B is a signed bit. So to represent value X, you're going to have three different values, B, V, and P, going to be represented, and the buffer. So we have V is the M-bit mantissa, and the way it's integrated is that this is going to be the most significant non-zero portion of the value, where 1 is going to be implicit, and then we store the next M bits of the value within the floating point representation. And the exponent P is also basically going to be power, or where in the range is the value is located, where the mantissa is located, and it is adjusted by the precision. So it's going to be an E-bit exponent, where this is the entire range of the values that are representable. In floating point representation, it could be single precision, double precision, but basically this indicates the lowest value that's representable, right, and the largest value. So this is the presentation for a floating point, and as we know that it's used in a large variety of different applications. So it has applications, say, in medicine, and defense, and economics. It's used, say, in machine learning, different types of computational geometry, physics, etc. And so what we're interested in the context of this work is doing computation accurately. So the idea behind floating point arithmetic that it's approximation. And what happens is there are certain scenarios when you run into errors, and those errors become significant, right? So a floating point is very good for actually doing the computation in many different applications, but the errors are unavoidable. That's because we have to truncate, right? We're not representing the entire value, we're representing a certain number of bits, and then there will be round off errors for each operation. But the issue is that those round errors can propagate, they can accumulate, and in certain cases that the errors can be even larger than the result itself. And so one application where this happens is that when you're doing a summation. So you have many numbers that you're adding, and they're significantly different in their magnitude. Some of them larger, some of them smaller, some are positive, some are negative. So when you add them together, it's possible for the largest values to cancel each other, and then what you get is small value that will be the actual result. But if you do computation one by one, like a binary, so you add two of them, then you add the next one to the result, you keep adding, it's possible that what you end up with is just the noise. You may end up with the arrow, and the value itself is not necessarily going to be particularly useful or precise. And so because of that, we would like to do something that's more accurate, something that's better. And from that point of view, is also floating point addition is not associative. meaning that if you perform computation on one platform versus another, you might get different results. And if you're using that in security applications, for example, like if you sign the result, then there's issues with reproducibility. So our goal is to basically have a more precise computation that starts with floating point representation and then does the computation precisely. And so what we want is something that's precise, but we also want to be able to do this securely on private inputs. All right, so there's certain applications where we seek both confidentiality of the inputs and we want accurate summations of many real numbers. And so if we look at that from sort of broad perspective, summation solutions have been developed, they're accurate, and they use like a different data structure for performing that computation, but they're not necessarily amenable to secure computation protocols because of their structure, right? I'm not going to look into that in a minute, but what we'd like to do is we'd like to develop a solution that somehow has similar nature, but will be able to easily translate into a secure computation protocol and do this operation securely and accurately. So I'm not necessarily going to introduce secure multi-party computation, right? So this is what this session is about, and we understand that there's no information disclosure during the computation itself. But what I'd like to mention specifically is that the secure requirements are such that the computation has to be data oblivious so that we have a hope of maintaining data confidentiality guarantees, right? And so what this means is that the instructions we execute, the memory locations that we touch, must be independent of the inputs themselves, right? The computation cannot depend on the data. And this is significant for our work because the algorithms need to be created in that way. So what we do in this work, our contribution is twofold. So the first one is we design a data structure that will permit us to do what we'd like to do, is the accurate summation of many floating point numbers without an error, right? So, the exact is the important part because we don't have any error. And then once we have this data structure and show that it has the desired properties, in our case it has to be exact, and then we translate it into a secure multi-party protocol based on secret sharing. And so what I would like to say is that the overall structure of the computation that we do is pretty straightforward. So at high level, when we get a large number of different inputs, so say we have n different inputs, the first thing that we do, we're going to take each value, convert it to a special representation, that superaccumulator representation, that's the data structure that we develop. Then perform exact summation on superaccumulators. And once we have that, we convert the result to the floating point value. So what I would like to say is that if you don't do anything complicated or non-trivial, it's always possible to have something similar where you start with a floating point representation, convert it to a very large integer, right, depending on the precision of a floating point numbers. So for double precision, it's going to be like 1,000-bit values. And then you can add them exactly, and then convert the result. The interesting part is that integer representation, the naive way of doing that, is not necessarily scalable. And what we do here is something that's going to be more efficient in terms of the performance. So this is the high-level structure. And what I would like to do is to go into just a little bit of detail and talk about the data structure itself and how we realize it into a secure protocol. So the superaccumulator data structure basically looks like an array, and we have certain bins, right? So if you think about floating point value, right, that there's a large range of possible exponents, and the mantissa lies somewhere in that range, right? And so what we do is we have the superaccumulators basically has bins that are size 2 to the w And in some way, this is a parameter. W is a parameter to the system that you can modify. It's also, for us, it's needed to show correctness. And this is basically a step of the computation. And then if you take one value, one floating value, convert it to the superaccumulator representation, for one of them, the mantissa is going to start at one point, and it's going to be written that way. For a different value, the mantissa is going to start in a different location. Everything else is going to be empty. All other bins are going to be empty. But for us to be able to use this representation to perform computation, we're interested in addition. The internal representation is not going to be W bits. It's going to be twice as long. So basically, the previous value, even though it was written consecutively and above, so that you can see the way it would be written, is actually only half of a bin is occupied, and another half is empty. And so once we add a lot of different floating point values, superaccumulators in this format that were originally normalized, then what we end up is with the additional values that exceed the original representation, and that portion will need to be moved and added to the next point, right? Whatever overflow happened is going to be a part of a different bin, and so basically once we add them all together, we need to move those values to the next bin, and this is what we show is the correctness is guaranteed if you have a certain bound on the representation versus how many values you're adding. And then the next part will be is to look at how we realize this sort of high-level intuition, and there's a couple of different interesting components that I would like to mention here. Is like one of them is aligning in an oblivious way where the sort of mantissas are going to go, right? Because we basically need to put it in the right place without having to disclose that location. There are certain things that we experimented with, like, for example, truncation. We considered a lot of different options to see which one would be faster in this setting. So we do everything in a ring setting to permit sort of more efficient computation. There is another one is binary to unary conversion that was previously performed over a field that we have a different implementation. And so all of these so far work for any number of computational parties for different thresholds. We have one component that is three-party, and this is conversion basically of a bit from a small field, from a small ring to a much bigger ring, and it has basically reduced the communication by a factor of 2 compared to what was available. And then once you perform the summation, you basically need also to normalize the result. You need to find the first non-zero position, right? Then copy it from there and store it as a mantissa, and this is where you get your result, right? So that there are some interesting algorithmic solutions that we get as a result of this work. And we're now at the end of our time, so I didn't include any sort of performance results here to keep you intrigued, so you have a motivation to go to the paper. But what I wanted to say is there's not necessarily any other work that did exactly the same thing, so our comparison is still not necessarily equivalent to what we do versus what other people have done in the past. Right? Thank you.
Thank you very much for this excellent presentation. While the next speaker is being set up, we do have a question here in the chat from Ian Goldberg. So what do you mean by exact summation of floating point numbers, though? Each floating point representation is just an m-bit approximation to the true value. So if you add a large positive number and a large negative number with the same v and p, all you know is that the sum should have its p at least m smaller than the p of the large values that canceled. It's still going. But you don't expect the value should be exactly 0, even though the inputs were exactly negatives of each other.
Mm-hmm. Well, my hearing comprehension is not great. So basically, I'll basically need to go look at the question again to see exactly what the notation is and what the example is. But my point is that you have large positive value, then something really tiny, then large negative value. If you sort of add them in this order, then what you get in the beginning is the result is actually going to be lost because it becomes an error. If you rearrange the numbers, if you end up sort of adding them in a different order, you may actually get useful result if you happen to have two large numbers canceled, and then you start processing small numbers. So basically, the result may be different depending on the order in which you're doing the operations.
Thanks very much. I'm tagging you in the Zulip if you would like to address that question further in the chat. I do understand it's a pretty long question, so that's totally fine. All right.